as we are following a tsunami advisory that is happening and extending the entire length of the U.S. West Coast.
Breaking news tonight, we begin with a tsunami advisory remaining in effect for the entire west coast of the U.S.
The roar of the Pacific had been uncharacteristically quiet in the days leading up to the event. Off the coast of Oregon, in the shadowy depths of the Cascadia subduction zone, geological forces had been steadily building. Then, in the early hours of the morning, silence gave way to fury as a massive undersea volcano erupted, tearing open the seafloor with a violent convulsion. This explosive event triggered a chain reaction that would end in catastrophe for the Oregon coast. The United States Geological Survey, monitoring the seismic activity through an array of deep ocean sensors and satellite data, issued an immediate red alert, a signal reserved for the gravest natural threats, just as a tsunami born from the eruption began its deadly march towards shore. Before we start, smash the like and subscribe buttons for more updates. As the eruption thundered below the surface, a plume of gas, ash, and molten rock surged upwards through the ocean. The water above churned and frothed, forced upward by the sudden displacement of seafloor. Shock waves rippled through the Pacific, the ocean itself becoming a conduit for destruction. In the epicenter of the disturbance, pressure sensors detected a rise in sea level of over 25 feet within minutes, a clear and terrifying indication of an imminent tsunami. There was no time for hesitation. The red alert went out, sirens blared in coastal towns from Brookings to Astoria, and emergency response teams scrambled to initiate evacuation protocols. The tsunami formed rapidly, its leading edge curling like a giant watery fist. As it traveled toward the Oregon coastline, the wave built in size and strength, pushed forward by momentum and an undercurrent of geological violence. Within an hour, the wall of water, carrying the energy of an undersea detonation, struck land. The first areas to be hit were the low-lying beaches and inlets, where the ocean surged inland with devastating force. The sheer magnitude of the wave carved into the coast, obliterating natural barriers and sweeping across the landscape like a freight train made of salt water. This event marked a rare convergence of geological and oceanographic forces. Undersea volcanic eruptions are not uncommon in the Pacific Ring of Fire, but few generate such massive displacements of water in such a short time. The location of this eruption, close to the margin where the Juan de Fuca plate is subducting beneath the North American plate, added an additional layer of danger. This is a region already infamous for tectonic instability, and the volcano's violent awakening only exacerbated concerns about broader seismic activity along the Cascadia subduction zone. The red alert wasn't only about the tsunami. It was also a stark warning about the potential for future seismic disturbances that could follow in the eruption's wake. The USGS, working in tandem with the Pacific Tsunami Warning Center and NOAA, activated an intricate network of data relays and satellite monitoring systems to track the tsunami's progression. Tsunami buoys stationed along the ocean's surface detected the rise and fall of the waves, transmitting real-time information back to command centers. The scale of the wave, both in height and in width, surpassed even the most aggressive models that had been forecasted in simulation drills. These models had long predicted the vulnerability of the Oregon coast to a large-scale tsunami, but even seasoned geologists were taken aback by the raw speed and intensity of what was unfolding. As the wave continued its inland march, it found no uniform geography. The contours of the Oregon coastline, its cliffs, estuaries, and harbors, acted either as barriers or funnels, amplifying the damage in some areas while sparing others. Cannon Beach, with its wide shoreline and flat terrain, was among the hardest hit as the wave penetrated deep into the town. Meanwhile, areas flanked by high cliffs like parts of Yakuts saw some deflection of the wave's energy, though they were not entirely spared from flooding and infrastructure damage. But the geological signature of the tsunami was consistent. A violent influx of water, delivered with almost incomprehensible speed and force, reshaping the coastline in real time. The implications of the USGS red alert rippled far beyond the immediate zone of impact. While the alert was geographically specific to the Oregon coast, it triggered a regional and even international cascade of monitoring. Agencies from British Columbia to California heightened surveillance along their own coasts, fearing that the seismic activity responsible for the volcanic eruption might not be isolated. Further afield, countries across the Pacific Rim paid close attention, knowing that tsunamis do not obey political boundaries. Every coastal nation on the Pacific Plate has experienced the wrath of the ocean before. This was a grim reminder that nature's power remains untamed. The eruption itself was unlike any recorded in the region in recent memory. Using remote sensing data, USGS volcanologists were able to piece together the eruption's timeline and mechanics. The initial event involved a rapid buildup of magma just beneath the ocean floor. As pressure mounted, the crust fractured along a previously unmapped fault line, releasing an explosion equivalent to several megatons of TNT. The seafloor collapsed inwards, creating a caldera and triggering a vertical displacement of the water column above. It was this movement, abrupt and massive, that unleashed the tsunami. Unlike earthquakes, which radiate energy through solid rock, underwater volcanic eruptions transfer energy through the medium of water, making their impact on coastlines both sudden and unforgiving. Another factor complicating the scenario was the composition of the volcano itself. Preliminary analyses indicated that it was rich in volatile gases like sulfur dioxide and carbon dioxide, which exacerbated the explosiveness of the eruption. These gases, under extreme pressure, burst forth in an expanding cloud that, while mostly contained beneath the ocean's surface, did contribute to atmospheric perturbations detectable by weather satellites. There is growing concern that such underwater eruptions could also contribute to longer-term changes in ocean chemistry, particularly in localized zones of low oxygen or increased acidity, potentially affecting marine ecosystems for years to come. From a geological standpoint, the tsunami was a case study in the interplay between tectonics and volcanism. The close relationship between the subducting Juan de Fuca Plate and the North American Plate creates a fertile ground for volcanic activity, but it also means that stress is constantly accumulating along fault lines. This eruption may have released some of that stress, but it also introduced the possibility of increased seismic volatility across the region. The USGS has already begun intensifying seismic monitoring in the area, watching closely for signs of aftershocks or triggered earthquakes. Emergency response teams faced a harrowing challenge as they raced against time to evacuate coastal areas. The Red Alert system, automated yet responsive to real-time data, served as a critical line of defense. In some towns, people had as little as 20 minutes to flee to higher ground. That such a warning system existed at all was the result of years of investment in earthquake and tsunami preparedness, investments that, on this day, proved to be life-saving. Still, the event exposed weaknesses in evacuation routes, particularly in older communities where infrastructure had not been modernized to account for such rapid movement. The psychological impact of the tsunami's arrival was immediate and visceral. Residents who had lived along the coast for generations described the ocean as turning against them. Where once there was a horizon, there was now a towering wall of water. The powerlessness of the moment, watching the wave approach with no option but to run, will leave scars long after the waters recede. For those who survived, it will remain a defining experience, a moment when nature's supremacy was made horrifyingly clear. As the waters began to pull back, exposing the torn earth and ruined structures beneath, geologists and oceanographers took to the skies and the sea to study the aftermath. Though this moment marked the climax of the tsunami event, the eruption itself was still unfolding. Lava continued to vent from the fissure on the ocean floor, building new mounds of rock and altering the local seabed topography. Hydrothermal vents erupted around the edges of the new caldera, expelling superheated water and minerals into the surrounding ocean. These conditions created a dynamic and hazardous environment for research vessels attempting to map the post-eruption seafloor. Satellites circling overhead tracked the dispersal of volcanic ash and gases into the upper atmosphere. While the bulk of the eruption's material remained submerged, some of it breached the ocean's surface in the form of steam plumes and aerosol clouds. These emissions were absorbed into prevailing wind patterns, and meteorologists began tracking the potential for acid rain in downwind regions. Though not catastrophic in scale, these environmental side effects represented yet another layer of complexity introduced by the eruption. Fisheries along the Oregon coast, vital to the local economy, braced for ecological disruption. The force of the tsunami had not only devastated infrastructure, but it also stirred up deep layers of sediment and pollutants, potentially leading to fish kills and contamination of breeding grounds. The combination of underwater volcanic ash and coastal runoff introduced an unpredictable element to water quality, raising concerns among environmental scientists about the longer-term health of marine populations. The red alert issued by the USGS functioned as a critical mechanism not only for real-time response, but also as a call to reevaluate preparedness protocols. Scientists and emergency planners alike recognized that while the system worked, it was tested to its limits. This event highlighted the need for even faster data integration, more localized warning systems, and resilient infrastructure capable of withstanding tsunami force. Investments in vertical evacuation structures, engineered platforms built to allow people to climb above tsunami levels when there is no time to flee, may now take on renewed urgency along the Oregon coast. On a broader level, the event served as a potent reminder of humanity's vulnerability in the face of Earth's internal processes. Despite all technological advances, the planet retains the ability to shock and awe in ways that defy prediction. The ocean, which so often represents calm and continuity, revealed a ferocity born of fire and pressure. And from this violent upheaval came a renewed awareness that beneath the surface of our blue planet, forces are always at work, often unseen, sometimes deadly. Communities along the Oregon coast will spend years reckoning with the consequences of this event. But for scientists, emergency managers, and policymakers, the eruption and resulting tsunami serve as a critical data point, proof of what happens when volcanic forces act in tandem with oceanic dynamics. It is a rare event, but not a singular one. With tectonic plates continuing their inexorable motion beneath the Pacific, there will be other eruptions, other waves. The task now is to study, to prepare, and to remember. The USGS Red Alert was more than a warning. It was an acknowledgement of the scale of what had happened, a signal to the world that nature had reminded us once again of who holds the true power. The sudden ferocity of the tsunami that slammed the Oregon coast was only the surface manifestation of a deeper and more ominous shift beneath the Pacific. Beyond the eruption and the immediate waves it created, this event has catalyzed a reckoning within the scientific and emergency management communities. It is now clear that undersea volcanic activity near the Cascadia subduction zone can initiate far more complex and aggressive outcomes than previously assumed, prompting a new era in modeling and forecasting these threats. The extraordinary violence of this particular eruption redefined expectations for how such geological events behave, and reinforced the understanding that the Pacific Northwest sits precariously atop one of the most volatile tectonic environments on Earth. Research institutions across the globe began an urgent analysis of the data pouring in. The eruption's seismic signature revealed patterns previously undocumented, long-period tremor waves interspersed with high-frequency bursts, suggesting not only a massive explosion but also deep crustal fracturing. This information is pivotal, as it raises the possibility that magma may now be migrating through previously stable rock layers, increasing the risk of future eruptions or even triggering secondary fault slip events. The question scientists are now asking isn't just how this volcano erupted, but whether it could be the first of a series of related volcanic or seismic episodes. The mechanics of stress transfer from volcanic to tectonic systems remain a complex puzzle, but this event has provided a rare, if unwelcome, opportunity to observe those dynamics in real time. At oceanographic institutes, marine geologists are reevaluating the structural integrity of the seafloor near the eruption zone. The caldera formed by the collapse of the volcano has dramatically altered the bathymetry of the region, changing ocean current patterns and affecting everything from sediment transport to the behavior of marine megafauna. Large undersea landslides precipitated by the blast and the reshuffling of the oceanic crust release their own shock waves through the ocean, potentially contributing to the tsunami's unusual wave profile. These submarine landslides are now being studied as potential independent triggers of localized tsunamis, forces that could one day combine with volcanic or seismic events to produce hybrid disasters far more devastating than either cause alone. Government agencies, faced with the enormity of what just occurred, are initiating reviews of critical infrastructure throughout the Pacific Northwest. Bridges, coastal highways, ports, and energy facilities are being audited for resilience to wave loading and soil liquefaction. The eruption's force was such that some offshore drilling platforms and ocean-based research stations reported structural damage from underwater shock waves alone. This raises concerns not only about the vulnerability of coastal infrastructure, but also about the adequacy of our offshore monitoring equipment. If these assets, designed to withstand the ocean's normal fury, can be compromised by a single event, then much of the region's observational capacity may be more fragile than expected. The shipping industry, too, is facing the repercussions of the tsunami's impact. Several cargo vessels that were en route to and from the port of Portland were forced to divert or anchor far offshore, avoiding potentially treacherous currents and debris fields churned up by the tsunami. Wreckage from destroyed piers, fishing boats, and coastal buildings was carried far out to sea, creating maritime hazards that may persist for months. Insurance companies and maritime regulators are working in tandem to assess risk exposure, and shipping routes are likely to be redrawn in the short term to avoid the unstable zones near the eruption site. These disruptions highlight just how interlinked natural disasters are with economic systems that depend on predictability and safe passage through ocean channels. From an ecological standpoint, the undersea eruption's consequences are expected to echo for decades. Volcanic gases and ash have introduced high levels of sulfur and heavy metals into the water column near the eruption site, potentially poisoning ecosystems within the immediate blast radius. Sensitive coral beds, deep-sea hydrothermal vent communities, and migratory fish populations are all being monitored for stress signals. Marine biologists are particularly concerned about plankton blooms caused by the sudden nutrient surge from the eruption. While these blooms might temporarily boost certain fish stocks, they can also deplete oxygen in the water, leading to hypoxic zones that are lethal to marine life. What was once a thriving underwater habitat may now be transitioning into a dead zone, changing the region's ecological balance. Meteorological models have also been subtly impacted by the event. Although the volcanic ash plume did not reach the stratosphere in significant quantities due to the eruption's submarine nature, steam and aerosols have interacted with atmospheric systems above the Pacific. This could affect cloud formation, localized weather anomalies, and even jet stream behavior in the coming weeks. The precise role of underwater volcanic events in influencing climate and weather is still a subject of active research, but there is increasing evidence that large eruptions, especially those with sustained venting, can perturb regional weather patterns in unpredictable ways. Meanwhile, engineers are racing to deploy improved monitoring instruments across the seabed near the site of the eruption. Deploying these tools is both urgent and dangerous. Robotic submersibles equipped with LiDAR, sonar, and chemical sensors are being dispatched from oceanographic vessels to map the altered terrain. These vehicles are tasked with identifying new vents, measuring thermal gradients, and detecting the presence of additional magma reservoirs. This effort will help determine whether the eruption was a singular event or part of a larger magmatic intrusion that could destabilize surrounding geological structures. A particular focus of study is how pressure dynamics at depth interact with water pressure to either suppress or intensify volcanic explosions. Unlike terrestrial eruptions, which expel ash and lava into the air, underwater volcanoes must overcome the crushing weight of the ocean above. This dynamic makes them less predictable but no less dangerous. In fact, the containment provided by water can sometimes allow pressure to build to far more catastrophic levels, as was the case in this eruption. Understanding these dynamics will be crucial for improving early warning systems, especially in densely populated coastal areas where even a few minutes' delay can spell the difference between safety and tragedy. The psychological and cultural dimensions of this disaster are also beginning to surface. For indigenous tribes along the Oregon coast, the tsunami may resonate as a validation of ancestral knowledge and oral histories that speak of great waves and angry mountains beneath the sea. Some elders had long warned that the land and ocean were due for a reckoning, and this eruption may now rekindle discussions around traditional ecological knowledge and its value in modern risk mitigation planning. Conversations are beginning about how to integrate indigenous land use practices and perspectives into state and federal disaster preparedness strategies, potentially forging a new paradigm of shared stewardship between science and culture. Educational institutions, particularly those in Oregon and neighboring states, are shifting their curricula to address the implications of the event. Earth science classes are incorporating real-time data from the eruption, and public lectures are being organized to help communities understand what happened and what it means going forward. The suddenness and severity of the disaster have renewed interest in STEM education focused on geoscience, environmental monitoring, and civil engineering, fields that will be essential in preparing for future threats. The role of social media and digital communication in this crisis also stands out. Within minutes of the red alert being issued, posts began flooding online platforms with video footage, drone images, and first-hand accounts. While this spread awareness quickly and helped some residents reach safety, it also fueled panic in areas that were ultimately unaffected. Algorithms that amplify the most dramatic content led to a flood of misinformation and speculative theories. In the wake of the eruption, tech companies and emergency management agencies are now collaborating to refine automated alert systems, prioritizing clarity, accuracy, and geo-targeted messaging. In future events, real-time data must be delivered in a way that informs without overwhelming or misdirecting the public. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the tsunami? Do you expect more eruptions or alerts soon? We want to hear from you. Thank you for watching, and see you next time.